So far we've been looking at the stability of a one variable system, focusing on y stability, and now we're going to look at two variable systems. And there's a neat trick to understand their stability using the sometimes called a phase portrait or a phase plane. That is a way to depict the steady states and the dynamics of the system that immediately visualizes the stability. Okay, so we're going to look at two variable systems. So let's say variable x and variable y. Right, and the rate of change of x and y, so dx dt and dy dt, are determined by the balance or the imbalance that exists between their synthesis and degradation rates. Right, so if x is synthesized faster than it's being degraded, it goes up, and the other way around. And the rates of these synthesis processes and these degradation processes, of course, can depend on x and y. So you get something like this, right? So the rate of change of x depends on x itself and on y. And the same for the rate of change in y. It also depends on x and y, because some of the synthesis and degradation reactions can be dependent on x and y. So, for example, you can look at this case. Alright? This is a really simple example that it's easy for you to solve by hand. So, we know now, so what could be the case? There could be values, right? So let's say that values of x and y, so concentrations of x and y, exist that make fx equal to 0 and g equal to 0, right? And those we would call clearly the steady states, right? So this is where the x dt equals 0, but also the y dt. So we would call them steady states. And there might be multiple of these steady states, of course. We've already seen this in the one variable example. There is no reason to believe that there could not be more than one, especially in the case of bistability, right? Then we know we get 3. But there might also be values of x and y where fxy equals 0, but g is not 0. Or where g equals 0, but f does not. Right? And so these values, they specify the curve f, right? Because they're constrained by f and constrained by g. And only at the steady state, right? Only at the steady state values of x and y, they're both 0. So what we can try to do, we can try to plot the values of x and y where f is 0 and the values of x and y where g is 0 in a plot with x and y on the axis, right? So we get two curves, one for this equal to 0 and the other one for that equal to 0, and where they intersect we have the steady state, and then we can see whether that steady state is actually stable, right? So let's do that for this this example. Okay, so right. So let's set this to 0. So let's determine the fxy for 0 relation. And we plot that. If we plot that, we want to solve that for y. So that means that y is just equal to x divided by 1 plus x, right? At all these values, f is 0. So that just means that something like this. So this is y equals 1 plus 1 plus x. So effectively, this is f at y equals 0. And that is called the null climb of x. So i.e. dx dt is 0. So the null climb, so that means that no change in x, so this is the dx dt equals 0 condition. So that's this curve, it's the null climb of x. We can also determine the null climb of g of y, and that is the relation between y and x that makes g 0. So we have to do 1 plus 1 plus x equals y divided by 1 plus y, right? And so we want to solve that, so that means that 1 plus y equals y times x. So that means that 1 equals y times x. So that means that y equals 1 over x. Yeah. So this is the null climb for y. And this is the null climb for x. So the null climb for y goes like this. So y equals 1 over x. This is where gxy equals 0. Null climb of y. Okay, so here we have the steady state, yeah? Okay, so let's figure that out. So what is the steady state value? Well, we know that y equals x plus 1 plus x at the steady state value, and y also equals 1 plus x, right? Okay, so that is what happens here, because then both of these relationships are true. So that means that x divided by 1 plus x equals 1 over x. So that means that x squared equals 1 plus x. So that means that x squared minus x minus 1 equals 0. Okay, so we want to find values of x where this is true. So let me double check whether I've done everything correctly. So 1 over x, yeah, exactly. Okay, so we need to solve this equation for x, and then we get the steady state value. So let me do that. And it turns out that this is true for a value of x equal to 1.62. So if you throw this in and solve in Mathematica, then x is equal to 1.62. So there's a steady state, 1.62. What is then the value of y? Well, 1 over 1.62 is the value of y. So what is that? 1 over 1.62 is 0.62. So the steady state of y is 0.62. Okay? So let's think about this for a moment. So what we know is that along this line, right, y equals 0. So there is no change in y. And along this line, x equals 0, so there is no change in x. Okay, so that means that if I'm at a point here on the null line of x, that x cannot change, so y can only go up or y can only go down. Yeah? And on a point on the y null line, y cannot change, so y will remain the same. So x can only go up or x can only go down. In this point, they are both equal, okay, to 0. So then in that point nothing happens, but this point doesn't need to be stable, so it could be that close to this point, right, the dynamics goes away. So what we want to figure out is that so if you start at a certain starting value of x and y, so let's say here, what happens to the value of x and y at the next time point, right? So let's say we are here, so at x0, y0, yeah? And we want to know what is the value of x at time dt later, right? Okay, what is that value? Well, that is going to be x0, right? Of course, plus the change of the x dt at x0, and this change in the y dt at y0, right? So that's the new point. So let's say that neighboring point is there. Okay. So this means that there was a change in x of this value, dx, and there was a change in y of that value, dy. And that happened in a time step dt, given the starting value x0 and y0. So now you're at dt, comma, y dt, right? So in fact there is this arrow. And this arrow tells you the change in x in time dt and the change in y in dt. And x went down and y went down. Okay? So you can, in every point, you can draw this arrow. And this arrow, the net arrow, is the combination of the change in dy, the change dy and the change dx, which are the concentration changes in x and y in a small time step. So what you can do, you can determine these arrows throughout this plane, okay? And that's something that you can do in Mathematica with stream plot or with vector plot, okay? Now we also know that along this curve, x doesn't change. So y changes can only be that way or that way. And along this curve, so along this curve x doesn't change, and along this curve y doesn't change, so x changes can also only be towards it or away from it. So there are certain rules by which you can reconstruct this curve, and now the question is, how do the arrows point to this steady state? If they point like this, right, then the system is stable, but if the arrows would point outward, then the system would be unstable. Okay? So drawing the null lines, identifying the intersections, and identifying these arrows that represent the direction of the system in which it moves to at a certain state of the system. So if the state of the system is here, then you look at its corresponding arrow, and then you know whether x and y go up or down, and what their combined change is, such that you know the next state of the system at the next moment in time. So making a plot with these arrows and these multiplying is called a phase portrait. And in the syllabus it is shown how to do this in Mathematica. Okay, and now, so that means that also visually you can now assess the stability of steady states by looking at the possible value, at the directions of these arrows. And that means that we can also distinguish the nature of steady states by arrows. So it could look like this, it could look like that, or it could look like this. There are all kinds of options, right? So you can classify steady states according to the flow patterns around these steady states. And that's something that we're going to do later. Now, rather than looking at the flow patterns around these steady states, you can of course also determine the eigenvalues at that point. And that's what we're going to do in the next lecture. Okay, and as soon as you know these eigenvalues, you also know exactly the flow patterns around this steady state. So these things are, in fact, these things are related to each other. Okay, so this means you now know what a phase portrait is. It applies to two variable systems. It has null lines associated with these lines. And these null lines correspond to one differential equation B is 0, but not the other one. The null lines intersect at steady states. These arrows indicate the direction of dynamics at a certain state of the system. And the arrows close to steady state values allow you to identify whether a steady state is stable or not. Okay, that's it. Thank you.